Hello everyone, I'm Donghe Kang from the Ohio State University. Today I'm going to introduce our work, Jigsaw, which is a table partitioning and a query processing engine in the relational database. The second author, Ruochen Jiang, is my lab mate, and the third author, Spiros, is my advisor. So in this talk, I will first introduce a new table partitioning technique, the irregular table partitioning. And then we find that the existing query processing algorithms cannot be directly applied on the irregular partitions. So we propose a new query processing algorithm, the partition at a time method. And at the end, I will show some experimental evaluation results. We find that evaluating queries on the irregular partitions is faster than on the other partitioning storage layouts in many cases. There are three table partitioning algorithms in the prior work, which are the horizontal partitioning, vertical partitioning, and hierarchical partitioning. The horizontal partitioning is widely applied in many systems, for example, the OLTP, OLAP, hybrid transactional and analytical processing. The goal here is to store tuples that are accessed together in one horizontal partition. The vertical partitioning stores attributes that are accessed together in one vertical partition. A plain column store is the simplest of vertical partitioning system where a vertical partition stores an attribute. The hierarchical partitioning fragments the table on one dimension first, and then fragments the table on the other dimension. For example, the Peloton system first horizontally and then vertically splits the table, and the GSOP work first vertically and then horizontally splits the table. Now let's discuss the limitations of these partitioning algorithms. Assume we have three queries accessing different table cells marked by three different colors. So the question here is how we partition this, how this partitioning algorithm split this example table according to the access pattern of the three queries. The horizontal partitioning algorithm splits the 6 tuples to 2 horizontal partitions according to the 3 queries. And we find that these queries, for example, the first one, it reads redundant attributes when the horizontal partition is stored in row major order and reads redundant tuples when the partition is stored in column major order. The vertical partitioning splits the 6 attributes to 3 vertical partitions, and the second query visits 2 vertical partitions. It reads redundant data from the leftmost vertical partition and has to reconstruct tuples across the 2 vertical partitions. The last one, hierarchical partitioning, creates many rectangular partitions. These hierarchical partitions are smaller than the partitions in other algorithms because the hierarchical partitioning fragments the table on both dimensions. As a result, we may need a large amount of small IOs to read these hierarchical partitions, and these small IOs underutilizes the disk bandwidth. Second, the last query still reads some redundant data. In this paper, we propose a new table partitioning technique, the irregular table partitioning, to store cells that are accessed by the same query in one irregular partition. Here we generate 4 irregular partitions. There are some unique features of the irregular partitioning. First, we can see that these partitions have different shapes, but partitions in other algorithms have the same shape, the rectangular shape. And it's worth noting that different attributes or tuples are partitioned differently. For example, attribute A2 stores the tuple T1, T2, and T4 together in the red partition, but attribute A5 stores the tuple T4 with T5 together in the green partition. As a result, evaluating these 3 queries on the 4 irregular partitions doesn't read any redundant data. The following features is connected with how we physically store one irregular partition. We can see that the tuples in one irregular partition have different schemas. And so the irregular partition is larger than the rectangular partitions because one irregular partition can store more tuples. So we could avoid these small IOs. When we physically store one irregular partition, we first reorder these tuples to store tuples with the same schema together row by row. So we store T4 with T5 together by storing the value 54, 64, 55, and 65. Because we store one irregular partition in row major order, we could reduce the tuple reconstruction cost in each irregular partition. Until now, we have seen the motivation of the irregular partitioning. The question here is how we generate these irregular partitions according to the query history of one table. Here is one algorithm with three phases: the partitioning phase, resizing phase, and the selection phase. The partitioning phase recursively splits the table to many rectangular partitions, and the resizing phase merges these small rectangular partitions to larger and irregular partitions. And at the end of the resizing phase, we generate many irregular partitions, but we find that evaluating queries on the irregular partitions is not always faster than on the existing partitioning storage layouts. So in the selection phase, we estimate the end-to-end query evaluation time on the irregular partitions and on a plain column store, and picks the most efficient storage layout. Now let's first introduce the partitioning phase. So the partitioning phase starts by taking the entire table as one rectangular partition and try to split this partition by different queries. So we try to query Q1 first and split the table to 4 partitions. The leftmost right partition is the attribute A1 that Q1 scans to filter tuples, and the second right partition is the cells that Q1 projects. So evaluating query Q1 on the 4 partitions, we do not read any redundant data. By applying the same methodology on the other 2 queries, we generate 3 partitioning candidates in total, and then we define a cost model to estimate the I/O time of the 3 queries on the 3 partitioning candidates. We pick up the most efficient partitioning candidate with the minimal estimated I/O time of the 3 queries. So we generate the 4 partitions shown in the right of this slide. We continue to split the 4 partitions until further partitioning cannot reduce the estimated I/O time. At the end of the partitioning phase, we generate many rectangular partitions shown in the left of these slides. And then in the resizing phase, we merge these rectangular partitions with the same access pattern to the larger and irregular partitions. There are 2 benefits of the merging. First, we could reduce the small I/Os to these rectangular partitions. And second, we could reduce the tuple reconstruction cost across the rectangular partitions. For example, evaluating query Q1 on the 2 right rectangular partitions, we have to reconstruct 3 tuples. But on the right irregular partition, we do not reconstruct any tuple because all the required cells is already in the irregular partition and the partition is stored in row major order. Until now, we have shown why and how we generate these irregular partitions. Next, we are going to discuss the query evaluation on these irregular partitions. There are multiple query processing algorithms in the prior work, which, for example, the tuple enter time in the PostgreSQL and MySQL systems, and the operator enter time method in the MongoDB system, a plain column store. However, both popular query processing algorithms assume that the tuples that are stored in the same order across different attributes. For example, in MongoDB, the first cell in attribute A1 and the first cell in attribute A2 must belong to the same tuple. However, this assumption is not correct in the irregular partitioning. So the 2 popular methods may read one irregular partition by multiple times. Here is one example. Assume we want to evaluate this query on the 3 irregular partitions in the column store using the operator and the time method. So we start by the select operator to filter tuples and find the tuple T2, T3, T4, and T5 passing the predicate. So we then to read the attribute A2 and A6 of the 4 tuples and reconstruct them. So we read the tuple attribute A2 first, tuple by tuple, and then read the attribute A6 of the 4 tuples. Here is the I/O trace of these operations. We find that the partitions, for example, the partition P1, is visited by many times. For example, P1 is visited twice to read the tuple T2 and T4. However, if the memory size is not large enough to hold all these three partitions at the same time, we may read one partition from the code disk by multiple times. For example, we may evict the partition P1 from the cache before we read the tuple T4. As a result, we have to read the partition P1 from the code disk when we visit it at the second time. Repeatedly reading the partitions from the code disk will significantly decrease the query evaluation performance. So in this work, we propose a new query processing algorithm, the partition at a time method, to read one partition just once. We also start by the select operator, loading the partition P3 and filtering these tuples. And at the same time, we initialize an empty hash table and fill the four tuples to the hash table along with the attribute A6 because we do not want to read the partition P3 again. Then we go to the project operator, scan the hash table, find the missing cells, which are the attribute A2 of the four tuples, and identify the partitions storing these missing cells, which are P1 and P2. So we then scan partition P1 first, fill the missing cells in the tuple T2 and T4, and then read the partition P2, fill the missing cells in the tuple T3 and T5. And at the end, the hash table stores the query evaluation results. Our paper also shows two parallelization strategies of this algorithm. Until now, we have seen why and how we generate these irregular partitions and how to evaluate queries on the irregular partitions. Next, I'm going to show some experimental evaluation results. There are three experimental questions in the paper. This talk focuses on the first question, saying what is the relative performance to evaluate queries on the irregular partitions and on the other partitioning storage layouts. There are more experiments in the paper. In the paper, we compare the irregular partitioning with 6 baselines, which are the plain row store, a plain column store, the horizontal partitioning in row and column stores, and the vertical and hierarchical partitioning in the row store. And for the hierarchical partitioning, we first horizontally partition and then vertically partition the table. The Peloton system, published in Sigmod 16, also horizontally and then vertically partitions the table. This paper uses two benchmarks, a realistic benchmark TPCH and a synthetic benchmark HAP. And for the TPCH benchmark, we denormalize the database because both the irregular partitioning and these baselines focus on partitioning a single table. The same method, denormalization, is also used in the GSOP work published in VLDB 16. Now, let's first see the query evaluation performance in the HAP benchmark when the data is cold. Here, we let all the I/O requests read data from the cold disk. This will highlight the I/O impact when we compare the end-to-end query evaluation performance. There are multiple experiments in the HAP benchmark shown in the paper. For example, we change the query selectivity, query projectivity, number of query templates, and so on. But here we only show the selectivity experiment. Let's first compare the irregular partitioning with the column baselines, saying a plain column store, and the horizontal partitioning in the column store. We find that both baselines almost have the same performance, but the irregular partitioning is up to 4.2 times faster than both baselines. This is because we use multiple HAP queries, and different HAP queries filter tuples according to the values of different attributes. However, the horizontal partitioning in column H horizontally splits all the attributes in the same order, but different attributes in the irregular partition are partitioned differently. As a result, the column H reads almost the same amount of data as the plain column store, but the irregular partitioning reads much less data than both baselines. Now let's move to the row baselines. The row and row H baselines do not vertically split the table. So we have to scan the entire table all the tuples and all the attributes to evaluate the query predicates. So both baselines are the slowest storage layout in our experiments. The row V baseline vertically splits the table, so it only reads the necessary attributes, but it doesn't horizontally split the table, so it still scans all the tuples for the attributes accessed by the query. However, the irregular partitioning only reads the necessary tuples for the projected attributes. So the irregular partitioning is faster than the row V baseline. Next, the hierarchical partitioning first horizontally and then vertically splits the table. So the hierarchical partitioning has the same limitation as the column H baseline, saying all the attributes are horizontally partitioned in the same order. As a result, the irregular partitioning is still faster than the hierarchical partitioning. Now let's compare the query evaluation performance across different selectivities. We find that when the selectivity is low, the irregular partitioning is faster than these baselines because the irregular partitioning reads fewer tuples and fewer attributes. However, when the selectivity is high, saying 100%, the irregular partitioning has almost same performance or is even slower than these baselines. This is because the irregular partitioning and these baselines read the same amount of table cells when the selectivity is 100%, but the irregular partitioning reads more data due to the tuple IDs. Irregular partitioning physically stores the tuple IDs on the disk in each irregular partition, but these baselines do not store the tuple IDs. So the irregular partitioning may read more data when the selectivity is high. Now let's see the query evaluation performance in the realistic TPCH data. Here we show three baselines and find that the irregular partitioning is faster than these baselines because of the same reason as in the HAP benchmark. Something different here is that the column H is faster than the plain column store on the TPCH data, but both baselines have the same performance in the HAP benchmark. This is because the TPCH queries filter tuples according to the values of a common set of attributes, but the HAP queries filter tuples by totally different attributes. So it would be easier to horizontally partition the TPCH data than the HAP data. Until now, we have shown the query evaluation time when the data is called. Here, we change the number of tuples in the HAP benchmark so that the table can fit in memory when there are few tuples. We find that when there are many tuples, saying I/O dominates the execution time, the irregular partitioning is faster than the plain column store because it reads less data. However, when there are few tuples, saying the table fits in memory, the tuple reconstruction cost dominates the execution time. As a result, the irregular partitioning spends more time in the tuple reconstruction because it reconstructs tuples in the hash table, but the plain column store spends less time because it directly merges these attributes. So the irregular partitioning spends more time when there are few tuples. This is an interesting research question and could be a future work of Jigsaw, saying how could reduce the tuple reconstruction cost in the irregular partitioning but still reads less time than the other partitioning storage layouts. Now let's briefly conclude this talk. We first introduced the irregular partitioning to generate these partitions with arbitrary shape. So we could read less data and can avoid many small IOs. As a result, we could save the IO time. Then we propose the query processing algorithm for the irregular partitions, the partition at a time method. It reconstructs tuples in the hash table, so it only reads one irregular partition just once. We compare the irregular partitioning with 6 baselines and find that the irregular partitioning is up to 4.2 times faster than a plain column store in the HAP benchmark. Well, thanks for watching and please read the paper for more details.